This is a game created by Ampligence called Hero and Cowards. So the basic idea is that every particle here is a agent, and they have two kinds of personalities. The hero will stand before the friend for the enemy, and the coward will stand behind the friend to avoid the enemy. And every agent here has one enemy and one friend randomly selected from others. And immediately after I play this game for the first time, I made the conjecture that uh, the final result is not directly sensitively depending on the initial spatial distribution of the particles, which is randomly generated. And also remember that uh, the the friends and the enemy choice are also randomly generated. So why I made the conjecture is because that from many years of studying physics, that kind of goes into the intuition. For example, as you can see, I just replayed uh, this simulation, and you'll again see all the particles goes into the steady state to the same point exactly again. So as you can imagine, yeah, you see this point. As you can imagine, this system is kind of chaotic. So tiny bit of error will produce is likely to produce different data, and nevertheless, the system goes to the same steady state, which means that uh, it's highly expected that the steady state doesn't sensitively depend on the initial condition. And moreover, uh, we can see that uh, we are playing different modes, and in this simulation, uh, although the initial configuration, the spatial distribution doesn't matter, it nevertheless goes into a steady state at this corner. At this corner. So, so intuitively, I would conjecture that the steady state doesn't depend on the initial spatial distribution, which is random. So, what else is cause this steady state, which is different from obviously different from this configuration, which goes into another steady state, as you will see. So I can actually speed up the process, and you'll see it more intuitively. So what makes this system configuration different from the other configuration? What made this configuration different from other configurations? What made this different from the others? It turns out that all those configurations are kind of randomly generated, and as you should recall, both the initial spatial distribution as well as the friend-enemy network were randomly generated. So because the computer system is using the so-called pseudo uh, randomness, that is why I can reproduce all those situations over and over again. And this one all goes to the corner, as you can remember. So since we made the conjecture that the initial configuration is not important, which means we're highly likely to conjecture that it is a topological network of friends and enemies, which is much more reasonably stable. Okay, so if you uh, might know, now the most promising quantum computing technology is actually called topological quantum computing, which is for the exact same reason that topological relatively stable. So if you don't know why I call this friend-family network to be topological, you can take a moment and think hard about it. They actually form a graph structure if you would. However, the funny thing is that in this system, we can actually perturb the system using my own fingers. So let me wait for the system to settle down into the center point, which is this only equilibrium in this particular system. So I can actually touch a point and drag, and now I am perturbing this space using my own fingers. Yeah, you can see this awkward motion going back, forth. They are actually caused by me because I'm actually dragging one of the particle here, which causes a chain effect that cause others to also move. As you can see, now I let go the system. It's going back to its original equilibrium, as you see. So let me use another system for example. In this one, you can clearly see that there is one leader which is leading the rotation, and the others simply follows, right? It's going corners by corners by corners. So you should expect if I just grab on this leader, this one particle should affect the entire system. And let me show you. Maybe just need to be fast enough to grab it. I'm trying to catch up to it. Yes, now I grabbed it. As you see, I am dragging it along. So now, what if I manually rotate the system counterclockwise using my own fingers? Or what if I manually dragging it clockwise? Now I'm changing it with my own fingers, and you can see this is the leader. Okay, so you should remember initially the system was going in this clockwise motion, which was a stable orbit of this dynamical system. But now what if I manually twist it backward to go counterclockwise? We should expect by symmetry that this is also a stable equilibrium. And I will let go this leader and see if the system will naturally settle down into this orbit. So now I let go my finger. Everything is happening automatically. As you can see, I twisted the system to go into another equilibrium by manually perturbing the system. So we can actually replay the system, and initially the system was going in the clockwise direction. And now I replay the system, and this is what happened initially. It was going in this clockwise motion. And if I grab onto this leader, the so-called leader particle, now I manually try to swing the particle in this counterclockwise motion and let go. Now, as you can see, it is going, the system is naturally going in this counterclockwise motion. But now I'm not perturbing the system at all. So this makes me think, what if I'm not playing with particles as a game? What if they represent actual human behaviors, like one leader is leading and the leader's action is actually causing other people's action to change? What if those are not just a flow of particles, but flow of people, or maybe the flow of money? What if this can be a simulation of the actual stock market? So let me use another example. In this one, all the particles stabilize into one line, right? What if I just manually drag around the particle and try to make them go in this way? Now this is another equilibrium. Just by symmetry, I just totally expect this is another equilibrium. Well, I can also drag this one downward. Is this equilibrium? And this one is not enough. This one doesn't have enough authority. So I'm using multiple fingers to do this. So I'm using multiple fingers to do this. So it's kind of funny. Sometimes if you just drag the leader particle, you change the behavior of the whole system. And you can see, yeah, this is another equilibrium. So just by symmetry, I should totally expect this dynamical system has 4 equilibrium, as you just saw. This is the 4th. And let me make it go back to the original. Yeah, this was the original equilibrium. So this is an illustration that by manually perturbing the system, I can experiment with the behavior of the crowds, and just simply because some people blindly follow other people. And most interesting, it is actually this dynamical system. So it's kind of periodic, but as you can see, it's going in now in a counterclockwise direction, right? Now it's going counterclockwise direction, and let me actually speed up the system. Okay, let me speed up. Now, yeah, let me actually speed up the system. So now you already see some kind of chaotic behavior. It sometimes goes into the counterclockwise direction. It sometimes goes into this counterclockwise direction. So just by my physics training, I suspect this system is truly chaotic by definition, like a typical chaotic system. And now it's being trapped or on the way to the so-called strange attractor, which is an attractor of fraction, decimal fraction dimension, which is not a whole number. It's not 1D, 2D, 3D, but possibly like 1 point something, 1.5, 1.3, 1.7 dimensional attractor. So now, if I manually intervene the system using my own fingers, let's see if I can cause the system to behave more or less chaotic. So there's one not moving particle, that is the one dragged by me. So I manually fixed 2 particles, which actually caused this chaotic system to stay in an equilibrium. Now if I just do it like this, yeah, just by manually holding 1 particle, 2 particles. Yeah, I need to, no, I just let go 1 particle. I'm holding 1 particle and let go 1 of the particle. Now the system is in a periodic motion. But if I just hold another particle, I suspect, yeah, I hold another particle, which I suspect the system now goes into a steady state. Yeah, I will let go the lower right one and see what happens. Yeah, the system goes into a kind of periodic motion, kind of periodic. Now I let go both particles. Yeah, you see, I'm holding this one. I let go both and see the system is now going to a chaotic back and forth, counterclockwise and clockwise motion. And if I just by watching, I kind of see this particle is playing some leading role. I don't know if you noticed that, but I kind of noticed the particle is playing some leading role. I need to slow down the system so I can catch it. need to slow down the system to catch it. Yes, I think I catched it. I don't know if I catched it. Now I catch two particles alone. Yeah, I think I cut the so-called leader particle, which stabilized the system. If I put those two particles into the same place, I conjecture the whole system will follow. Yeah, yeah. So so this is actually a good illustration how just by changing the behavior of the leading uh, particle, you can actually change the behavior of a big crowd. Yeah, you see. Yeah. So so just by changing the behavior of one important particle, I suddenly turn the chaotic system into non-chaotic, which is quite interesting. And the system is multi-touch, so yeah, I can use another finger to do this. So I am basically limited by how many fingers I have. So if I have another friend, I can do another particle, but which I don't now. So that's quite interesting. So what if, so the takeaway message is that this is now a very basic simulation. I did the programming in one day. But what if uh, this is not a simulation of a stupid game, but still a simulation of actually human behaviors or stock market behaviors. And we can try to perturb the system, intervene the system to see how the system can behave differently after the intervention. And maybe some intervention can prevent the crash of stock market. Maybe some intervention can cause the crash of stock market. We don't know, but by using human intervention in a visualized and intuitive way at a high bandwidth, we can do some research that was previously impossible. So, thanks for watching and see you next